Okay, so in this video I'm going to talk about the ABC conjecture. So this is the ABCs of the ABC conjecture. Okay, so oh, I'm connected to the Wi-Fi. Great. Anyway, so here's a conjecture. So this is given by so I think there's an E in his name, Osterley and Masser. So I know this is I know David Masser. I'm not too familiar with Osterley, but apparently Osterley gave it in a talk, and then David Masser kind of generalized it. And the conjecture is the following. It says that for every epsilon greater than 0, there exists some constant C epsilon such that for all triples A, B, C, and Z cubed, which are coprime, where A, B, C are coprime, so they have no common factors. Pairwise, they have no common factors, such that A plus B is equal to C. Then, so for all epsilon, there exists a constant C epsilon, such that for all triples A, B, C, so there's a little c, where A, B, C are coprime, and they have this, we have so it says we have the following: the maximum of A, B, and C is less than or equal to this constant times the radical of A, B, C to the 1 plus epsilon. Okay, so this is the statement. It's about the size here. So the whole, one of the philosophies is that it relates multiplication and addition. Okay, I need to give you a little definition here. So if n is an integer, the radical of n is equal to the product of the primes dividing it. Okay, so let me do an example, e.g., the radical of 2 to the third times 5 to the fourth is equal to 2 times 5. Okay, so it really doesn't care about these prime powers here. Okay, so this is the conjecture here. All right, let me give you some variants before we're talking about applications. So this is some variants. There's weak forms. So here, this is for a single fixed epsilon naught. Okay, so this is saying that there exists, i.e., there exists some epsilon naught, and there exists some constant C of epsilon naught. Okay, so like here, it said for all epsilon, and there exists some C epsilon, right? Here, it's saying we can just find it for a single one, like epsilon naught is equal to 1. Okay, and then there's kind of these explicit weak forms, which are nice. Which are really kind of like, so here, this is for a single fixed epsilon naught. Fixed. And the constant is specified. Okay, and so let me give you an example. So this is the explicit form. So an explicit form when epsilon naught is equal to 1. Okay, so it says that Here the constant here says that C epsilon naught is going to be 1. So this, I found this in Bombieri-Gubler. In particular, it'll say that the max of A, B, C is less than or equal to the radical of A, B, C squared. Okay, so this is kind of really cool. So note that if A and B are positive, so these are positive integers, then what this is saying is that A plus B is less than or equal to the radical of A times B and then A plus B here squared. So it's kind of a really elementary statement here, just about arithmetic, right? You have addition, and then what's it saying? It says that when you add two coprime numbers, so A and B have to be coprime, that this sum is related to this radical here. And so this is really about the prime factors of A plus B. That being said, we can talk about, like, you can kind of see how it's related to the prime factors of A plus B. And I'm gonna now move to some consequences. And the first consequence of ABC. So the first consequence is going to be the what it says about prime factorization. So in this example, we're going to have A be p to the alpha and B be q to the beta, where alpha and beta, where p and q are coprime, are two distinct primes. And then alpha and beta are just some natural numbers. So, like, we're just looking at two prime powers here. And so by the explicit weak Fermat, so we have so p to the alpha plus q to the beta. And now we're going to do this, sorry, not Fermat, sorry, ABC. So we have this explicit ABC here. So this is one of the explicit versions of ABC. Okay, and we'll plug this in here. Okay, so now we'll take the radical of p to the alpha, q to the beta, p to the alpha plus q to the beta here, like this. Okay, and so this is less than or equal to, well, this is going to be p, q, and then we have the radical of p to the alpha plus q to the beta. Oh, we have the squared here. So this will be squared and squared here. Okay, so this is so did I put a square here? Yeah, I put a square. Okay, so this is this nice form. So what it says is that this thing here needs to have so let's say that these were like a billion, alpha and beta were huge, right? Then this would say that here, let's actually do it here. This number, when we add them, needs to have like large prime factors, right? Or needs to have like no multiplicity, or no prime power factors, right? To make up for the size, see that here, to make up for the size happening in the exponents there, this thing needs to have a large prime factor, or have no power factors. So it tells you about the factorization of sums of powers of primes. Okay, and I have an explicit example. So like a sub-example, I guess. So in this sub-example, we took P is equal to 2, Q is equal to 3, alpha is equal to beta is equal to 10. Okay, so we're going to look at the sum here of these two guys. So that now we're looking at 2 to the 10 plus 3 to the 10, and it turns out that this number is equal to about 60,000. I mean, the approximate size, well, I guess it does matter for one of the sides, okay? And it turns out that this is equal to 13 times and this prime number here. Okay, so here, what does it? What do we have? Well, it tells us that this is the large prime factor that we were looking at. So this is the large prime factor of 2 to the 10 plus 3 to the 10 that ABC predicts. Okay. Cool. All right. So let me give another kind of demonstration of the kind of power of this simple statement, and that's through Fermat's last theorem. Okay. So suppose, so I'm going to show, that ABC, so the weak form where epsilon naught is 1 implies Fermat. Okay, so let's do this. So let x, y, and z be coprime and satisfy, well, x to the n plus y to the n is equal to z to the n. So this is what we call a Fermat triple. Okay, so by the weak form of ABC with epsilon naught is equal to 1 and c of epsilon naught is equal to 1, we have, well, we have that z to the n. So let's say that these are natural numbers. Okay, so they're positive. Okay, z to the n is going to be less than or equal to 1 times the radical of x, y, x to the n, y to the n, z to the n squared. Okay, and now each of these x and y, so let's actually write this out. So this is equal to x, y, z squared, and each of x and y are both less than z, so this is less than or equal to z to the 6th. So this tells us that n is less than or equal to 6. Okay, that's really cool. Okay, so here we can already tell that n's less than 6, and then proofs for small primes for small n, and show no such solution exists for n greater than or equal to 2. Okay, so even Euler has a case, I think. So, does Euler have a case? I don't remember. Okay, so but this is the point. Okay, so like even this basic statement here. So this other statement about the non-existence. So again, as we recall, the Fermat's last theorem says that there's a non-existence of solutions of this equation for n bigger than or equal to 3. Sorry. Okay, and that's kind of the basic things of ABC. Thanks for watching.